Okay, good evening everybody. I hope everyone's having a wonderful day. So last day, we started talking about complexity and how we can count operations that help us determine and derive a complexity function. And what we were interested in is what that complexity function might look like. So last day, I showed you how we could count line by line the total number of operations that can occur, and we found out that linear search takes linear time because it performs a linear number of operations, at least with respect to the input size, which was n in that case. So before we proceed to do another example, I want to show you how, how we counted all those lines. Now, when the algorithms get more complicated, the approach of counting every line and drawing out a table can get very tedious and time-consuming. So it would be nice to have a simpler way of approaching this. So I'm going to show you one such method, and you'll find in this course I'll use this method very often. So the first thing I wanted to point out is last time, each time we counted the lines and we determined a total number of operations by introducing these constants. For example, so I numbered the lines, I wrote out a table with each of the rows. This is perfectly fine to do, but like I say, it can be a little bit cumbersome when the algorithm starts getting more complicated. But here's an interesting observation, is that a constant number of operations, each taking some constant number of operations or constant time, is in fact going to end up being a constant number of operations. So for example, if I have 3 operations or 3 lines that all do a constant number of operations, you would agree with me that they all in total are some constant number of operations, right? It's just that there's 3 sets, there's a collection of them, but they're all in total a constant number of operations. So what we could do is we could take advantage of that. So if I were to number these lines here, I can reference these lines and I can identify them in groupings of constant numbers of operations. So just as an example here, now I must stress that in the notes, I do give a full description, just give you a flavor for how you might draw this up. But I wanted to make sure I gave you kind of the big idea here. So the first thing I wanted to point out is that there's really kind of 2 main blocks of constant number of operations. There's this stuff. Sorry, at the beginning I do this assignment of I to be 0, and I have all of this afterwards, right? All of these and that, you'd agree with me, all of the lines I've highlighted here in red, all of those take a constant number of operations, correct? Last time, each one of these lines I gave a constant, I assigned a constant to how long they would take, or the number of operations that they perform. But this line also is a constant number of operations. So what I'm going to do is I'm going to group them all together, and I'm going to give those operations, because they're all a constant number of operations, I'm going to call that C2. So there's going to be C2 many operations that represents those 3 lines. Then, inside of my while loop, notice that I have this assignment where I assign I to be I plus 1. We know that that takes some constant number of operations to do. It's an addition and an assignment, right? But notice that this is inside of a while loop. So if I take all of this together, both of these together, if I wanted to count up how many times this line occurs, well, it's C1 times the number of iterations of this loop, right? The number of iterations of the while loop. Now, in the worst case, could somebody tell me how many iterations are there of this while loop where it performs this assignment? Could somebody tell me? Yeah, n would be sufficient here. So keep in mind, if you were to count up how many times this line happened, this one specifically, you could say, yeah, that's n plus 1. But remember, from our exercise we did last day, all it does is just have one little extra check, and it doesn't really affect anything from a complexity standpoint. It's just one extra iteration. It's just a constant number of operations at the end of the day. So all we really have to do is, if we think about this carefully, I just really have to count how many times this is happening with respect to the loop. And if you take that and simplify it down, you see, okay, it's C1 times this. But in the worst case, as you may see, we do this assignment here n times in the worst case. Because remember, in linear search, we scan from the left to the right. And when we hit off onto the furthest right side, remember, this is when x, the element, sorry, the key I'm looking for, is not in the array. So in this case, in the worst case, this is n. So now, if you derive your complexity function, all you do is you take the bits and pieces that I have here. I really have two bits and pieces here. I have I grouped together here. I've got C1 times n plus C2. So notice that this indeed is a complexity function that counts the operations. But here's the big thing I want you to notice. What's the function look like? Did I get the same kind of function as I did last time? It's the same. It's a linear function. But notice that this is a much simpler looking function, right? Because I suppressed all those constants. If you go back to the exercise I did last day, you'll remember that there was a whole bunch of constants just sitting outside here. And then I had some linear term times another constant, right? So notice that this is a much simpler complexity function to play around with. And if you've seen this, you'd be very compelled to say that this is big O of n, which we'll talk about this hopefully today. So could we just, question, we could just consider them as just a single constant. Yes, so what I'm saying is that notice that lines 1, so if I were to number them like 1, 2, 3, 4, 5, if I number them like this, notice that lines 1, 4, and 5 all take a constant number of operations. And you would agree with me that if I take some constant number of operations, and there's a constant number of those, that's still a constant number of operations. Then, so that's why I'm saying is I'm simplifying down the analysis. Because in our previous exercise, I gave each one of these a name, each one of the number of operations. But remember, all of those are still some constant number of operations. I just gave them a new name. Yes, a constant plus, say for example, I have 3 constants I'm adding. If I look at the end of the day, all of them are constant if I add them together. That's the big point here. So if you go back to the exercise we did with that table, you'll notice that you'll still end up with something that has a bunch of constants, then you'll have some constant times a linear term here. So notice that this is actually, you can arguably say that this is a much easier way of deriving a complexity function in the worst case, by just grouping them by using fewer constants. So are there any questions about this? So notice that all I did was I grouped together operations and I counted those, as opposed to counting every single line. You'll notice that this takes a lot less time to do. Okay. That's a wonderful question. So the C1 here, now keep in mind, you could have made C1 be the evaluation of all these conditions plus this if you felt like it, but it's not necessary. I must stress that, remember, our while loop, this evaluation here is still some constant number of operations. And if I accounted for all of those plus this, I'll still end up with a constant number of operations times the number of iterations of the loop, which at the end of the day will end up being some function that looks like a constant times a linear function plus another constant. So notice that By doing it this way, I never really have to worry about those specific details. All I've done is I've grouped them together by the relevant operations. Now, just to be very clear, just to clarify really this big point, is that if, for example, this while loop's condition was not a simple or primitive operation, you would have to put that and take that into account when you measure the complexity. So for example, if this didn't take, all of this didn't take constant time, that most certainly is something you'll have to take into consideration of how long it takes to compute it. Because that's not a simple or primitive operation. And in fact, and somebody's asking if we can use this method in assignment 1. In fact, I encourage you to use it, yes. I'm encouraging you to try using this approach on assignment 1. There's at least a few different ways you could approach analyzing for assignment 1. One's using a table, another one if you prefer using this approach. We're going to use this approach a lot in this course. But I recommend, this one will save you a lot of time if you find yourself fiddling around with the time complexity analysis. But remember, I recommend you take a look at my example in the notes. So I read out a little description of how I wrote this out in the notes. I want you to take a look at that, just so you can see how you could describe it. Yes, we will be doing another example of this approach in a moment with a little bit more of a complicated algorithm. So don't worry, that is coming very, very soon. But before we proceed, are there any other questions about what I did here with linear search? Any questions at all? Okay, so far generally things are going well. Okay, the question about loops, so nested loops. We're going to see an example shortly with the nested loop. So I can assure you, I'm going to be giving you some tools to deal with nested loops very shortly. So I'm hoping that what I'll be addressing shortly will deal with what happens with a nested loop. Okay. So if we're okay, so first, if we're okay with this, can I see 2 thumbs up? 2 thumbs up. Is everybody doing good? But yeah, I will be addressing nested loops here today. So for those that are working on assignment 1, that may be highly relevant. Just a heads up. So anyway, perfect. I'm happy to see that. So I want to talk a little bit about some tools that we might need for counting. Because notice that I count some number of operations all around here, but sometimes when I have operations that are dependent on control structures, such as our loops here, notice that this while loop, I knew how many times this while loop was going to iterate. It's because I understood what this algorithm does in the worst case. Now, what happens if you have a control structure like a for loop or a while loop, and then you have another for loop or while loop embedded inside it? Well, often those will depend on the variable that's on the outermost loop. So for example, you may have a loop where it's like for I is assigned to be some value, I is less than or equal to some value, I plus plus, and then you may have another loop inside where for j is assigned to be something, j is less than or equal to a something, plus plus plus, sorry, plus plus, we don't need an extra plus. The point is that you can have a nested loop, and I want to show you how you can deal with those, because those are going to be something we'll run into very often. So I'm going to talk about a couple handy closed forms for analysis. Is it okay if I erase this, by the way? I want to just kind of explain a couple of interesting little tools that we're going to use. Okay, wonderful. So I'm going to talk about a couple of the so-called closed forms. Now, you may or may not have heard of what a closed form is. But very often, when we're counting, we run into situations where we're not just counting a constant number of things. Often they depend on some input, which usually make the form of some finite sequence. For example, 1 operation, then 2 operations, then 3 operations, then 4, plus all the way up to some n number of operations. We run into this very often. We'll see actually an example today of such an example. So this is an example of a summation. And this sequence actually has a very special name. Does anybody know what this one's called? It's okay if you've never seen it before. Starts with an A. Yes, yes, exactly. It's the arithmetic series. So this is called the arithmetic series. So if you've never seen summation notation before, there's a lower limit and an upper limit. So the way you would read this is it's the sum from I is equal to 0 up to n of I. So what's happening here is you can think of it almost like actually it's quite similar to how you might think of a for loop if you had a variable I that increments by 1 every single time. So notice that I start at 1 because that's what the lower limit tells me because that's what I is. So it starts off as I is 1, then increments by 1, now I becomes 2, and so on, up until and including the final term, which would be the upper limit. So all it is doing is substituting in what I is in relation to whatever this is. This is called the summand of the summation. In this case, it's a really simple one. It's just I itself, but you can have many of these different kinds. So that being said, I want to just tell you that there's a very simple formula. This is what we call a closed form expression. So notice that this formula, so if I wanted to calculate this out, it's gonna, if I were to add them up myself, I'll have to perform some number of operations that depends on whatever n is, in terms of the number of operations I need to do. However, there's actually a much simpler formula for calculating this. It's just n times n plus 1 over 2. Now, first you might say, Dan, where did that come from? What is this, some weird magic? Now, I'm gonna give you a very simple motivation to get this. So here's the idea. So suppose that, for example, n is 4, and I start counting. So I start at 1 plus 2 plus 3 plus 4, like this. That box is a little bent in. Make sure you ask for a refund if that's your box, okay? You might ask, okay, so if I were to add up all of these boxes, how much would that be? Now I'm going to show you a very neat way of justifying this. You may or may not have seen this before. Now, if I wanted to compute that, here's a neat way you could come about it. So first, remember, along this dimension of this, how many boxes there are read row-wise like this? Well, there's n of them. And then watch this, watch this. I'm just gonna show you a neat picture and it'll help click, hopefully. So what I'm gonna do is I'm gonna add an extra box on top of here, but I'm gonna draw the exact same picture I have here, but I'm going to rotate it like I'm mirroring over the diagonal of this. So for example, I can draw out my boxes so I could fill in all of those gaps. But notice that all this is just a mirror image of the boxes I have here, but I just drew them out in green. But here's the interesting thing. What's the dimension? So, like, how tall is the stack of boxes now if you include the green ones? Yes, so in this case, if n was 4, then it would be 5, but you're most certainly, you'll see that it's n plus 1. But if I ask you, what's the area? So if you ask, okay, so if it's n times n plus 1, that's the total area of this entire rectangle. But the boxes in black are the ones I'm interested in. That's exactly half the area of this rectangle. And boom, there it is. Does everybody see that? That's a very sweet way of coming about this if you've never seen it before. So if you ever find yourself trying to think about where this comes from, here's a simple way of coming about it. So just think about computing the area of a rectangle and just taking its half. So if you ever find yourself just thinking about, okay, what was that again? This is a very easy way of coming about it. Just think, okay, it's the upper limit times the upper limit plus 1 divided by 2. Is that cool? When I first seen this, I was like, whoa, that's fun. Okay, so this is one closed form we're going to very frequently run into. So I'm going to expect you to get familiar with this one. because when you do analysis with our algorithms, you'll very often have it where we have a loop where there's another loop that's embedded inside it. And what's going to happen is that I term I have there may be a slightly different term than just I. It might be like I plus 1 or I minus 1 or something like that. And that will actually represent the number of operations that are going to happen in your innermost loop. So if we add up over all the iterations of the loop, we end up with the total count of operations. So that'll be how we use number 1 very often. So are there any questions about number 1? So this is one tool we're going to use very often. It's usually one of your best friends when you're counting nested loops. So the second one here I want to talk about, this is where you have a sum, but you know how many times, say, the number of operations occur on each occurrence. So suppose I have two integers a and b and some real number c, where a is going to be less than or equal to b. So just following the same rules I described with my summation, I start at I is equal to a, I go up to b, and I'm multiplying, sorry, I'm not multiplying, I'm adding the term c. So keep in mind, very often you'll run into the c being some constant term, or it will be 1 usually. So if you want to know what the closed form for this is, what you could do is notice that every single time this is happening, notice that this is c plus c plus c plus c plus c, and you need to know how many times this is happening. The number of times this occurs is b minus a plus 1. So that's where this formula comes from. You might ask, why the plus 1? Well, think about it. If I take b minus a, this will tell me the difference of two numbers, but I also count the upper limit of my sum as well, like if I were counting these as discrete objects. So that's where the plus 1 comes from. So all this is just, because keep in mind, you might know that you can take this c and you can throw it out in front of this. So if you ever find yourself looking at this and saying, okay, well, what does that mean? Well, another common thing you might run into is if I have a sum like this, you'll notice that every single time I'm adding c, but c is if I were to do this how many times, another way you can write this, it's like doing this. So I'm summing up 1, but how many times am I doing that? This part right here is my b minus a plus 1. And if you find yourself just wondering why this would be the case, just remember, this c term, think of it like if you had 4 there. So if I started this at some a and some b, and I keep adding 4, you'd agree with me that if I know how many times I'm adding 4, I could just multiply that by the 4 by how many times I'm actually adding 4. So are there any questions about this one here? These are going to be our two kind of best friends when we're counting things. Okay, so we're not restricting a and b to non-negative integers. So I should be kind of wary. Most of the time when we do this, we're going to be dealing with non-negative integers, but if my memory serves me correctly, this will work fine if we have negative integers as well. Just the point is that it has to be that a is less than or equal to b. Otherwise, we're going to end up with something all backwards. And that's not going to make much sense for us. But I encourage you to try for yourself and see if it makes sense. Let me know. Let me know. But you almost will certainly find that we'll just be dealing with positive or non-negative values, because we're counting up discrete iterations, which normally our loops start at 1 or 0. Okay, so if we're okay with this, I want to proceed to our next example, because we're going to use both of these tools to help us do the analysis. So let's head on over here. So the first thing I want to do is I thought I would pick up a sorting algorithm for us to play around with. Now, I know that you will have probably seen this sorting algorithm. If it has been a while, or if you haven't seen it before, that's okay. I'm going to show you what that algorithm will look like, and we'll do the analysis, and we'll derive the complexity function, and we'll express its big O respectively. So we're going to talk about insertion sort. Now, the big thing I want you to recall about insertion sort is that when I deal with insertion sort, remember the whole point here is that we're going to be sorting an array given to us of length n. And in insertion sort, we go from left to right, considering each element starting at the leftmost position. Each time we consider each successive position, what we're going to do is, if it's in a spot for which it doesn't belong, we shuffle it to the furthest left where it fits. So the whole idea is you're going to end up having it where we're going to be shifting over or swapping elements to make way for the element we're considering until it fits in the spot, and everything up to that point will be sorted just before where we initially considered. So that's why we call it insertion sort, because you're inserting each one of the elements by considering them left to right, so that when we put it in the appropriate spot, everything that's up in that position and prior to it, to its left, will be partially sorted. So before we proceed to our analysis, we got to talk about the worst case scenario for this algorithm. Now, does anybody recall what the worst case scenario for insertion sort is? What causes insertion sort to take its longest? Does anybody know? So can somebody describe to me a scenario where we get it to, yeah, so I see it in the chat. Yes. Very good. Very observant. So notice that, so if you don't recall, that's okay as well. I encourage you to convince yourself of this, is that with insertion sort, it's when the input is given to you in reverse sorted order. So instead of it being from smallest to biggest, it's biggest to smallest. So the reason why is because notice that every time I take a position and then I shuffle it to the furthest left for which every element in that position to its left is partially sorted. Well, every single time I do this, I simply insert it into the spot, but I have to move it all the way to the furthest left it can every single time. And that's why it causes the most work for us. So we're going to see that when we play around with the analysis. So I'm just going to say, so we want to maximize the number of iterations. We're going to see the algorithm very shortly here. I thought I would talk about this first. The number of iterations of the innermost loop, because that's the loop that causes it has varying behavior. So I'll write down what that is shortly here. Innermost loop. But as the chat was pointing out, observe that the worst case scenario is when A is in reverse sorted order. So it means whatever would be the sorted order of the array, I just give it to you that in backwards. That's it. So keep in mind, just as a reminder, so I will be writing out the pseudocode here in a moment. So first, does everybody understand the general idea of the game plan? So I'm going to give you the algorithm. We're going to derive a complexity function based on the worst case scenario. And then when we count up all those operations, we'll simplify, and then I'll try to classify it in terms of big O. So let's head on over here. I'm going to write out insertion sort. Now, like I said, you may or may not have seen it presented to you in this exact way. That's okay. Believe it or not, if you were to pick up the pseudocode or maybe the the algorithm that you've seen that's been called insertion sort, you should be able to carry out the exact same analysis that we're doing here. So just as a reminder, the whole idea here is that each time I consider which position from the leftmost to the right, I consider each position and then I swap it with each successive position until I find a spot where it is sorted. So let's write out the pseudocode here and you'll see what I mean by this. So algorithm, insertion sort. So I'm going to be given the array. Its length is going to be n. Input is going to be array A of size n. And its output, A sorted in non-decreasing order. So this is another way of me saying from smallest to largest. Okay, so let me just go back over here. Somebody was asking about going back over there. So while I'm doing that, I'm going to start writing down the pseudocode here just to give us a little bit of a heads up here, because I got to walk us through that. So somebody's asking, yes, that's exactly it. Somebody was asking, well, what about if the elements, like, why aren't you saying increasing order? It's because that's exactly the point. It's because there might be two elements that are equal to one another. They have equal priority or equal, what we call precedence, if I were to order them from smallest to largest. That's why. Wonderful, wonderful. So it's non-decreasing just simply means that if I were to like plot them out in terms of their importance from smallest to largest, some of them might have equal value. So you could get plateaus and then they could go up again. No worries. Did you get everything there? Just wanted to make sure. Okay. So excellent. No worries. So anyways, we're going to have ourselves a for loop. I'm going to start it at I is assigned to be 1. It's going to go up to and include n minus 1. And in this case, I'm going to set up the innermost loop by assigning x to be the value that's currently in A sub I. Because remember, I'm just going to consider the next element immediately follows the first one and see if I can fit it into an appropriate spot. Because there's no real point in considering the first element because there's no shuffling to the left when you have the first position. So while j is greater or equal to 0 and A sub j is greater than x, we're going to do the following. So you might ask, Dan, what is this inner loop going to be responsible for? That's for the shuffling. When we move the element from the position it's currently in, and we want to move it to the furthest left where it fits. This is the role of this innermost loop. So this first one is just to make sure I don't go past the first position of the array. The other one is to make sure I find the appropriate spot. So what I'm going to do is I'm going to have A sub j plus 1 is going to be assigned A sub j. So I'm going to shuffle over a spot to make room for possibly what I'm going to put into the spot. That would be originally there. And then I'm going to decrement j by 1. So j is going to be assigned j minus 1. And then I'm going to assign outside of this loop, I'm going to say that A sub j plus 1 is going to be assigned x. Whoops, I need to write down this as a sub I up here. We're missing the a sub I here. So keep in mind, remember, we're looking at the sorting problem right now. There's no key involved here. We're just sorting an array. Then this would end the for loop. And then I simply return a at the end. So like I said previously, remember, you got to think of it like I have my array, and we go from left to right. Now, if I start in position 0, I don't have any shuffling I need to move the position, with the element. I don't need to move it any more to the left, right? It's already in the first position. So by definition, it's already partially sorted if I only look at the first element so far. It's when I bring the second element in, that's why we start at position 1. Is that I might have to swap the first position with the second position in the array. Or another way you could look at it is I'm going to try to put the element in the second position into potentially the first position, and I'm going to shuffle everything over by 1. So for our purposes, this is just the insertion sort for our little exercise here. And what I would like to, yes? It's inside. Yes, so this is just inside the while loop. Yeah, so this line right here, that's inside of here. My apologies. It's kind of a little close in there. I'm sort of running out of space. I'm like, oh no. No worries. No, thank you for asking. It's important to clarify that. Okay, I'll give one moment. Yes, this is inside the for loop. Yeah, this is inside the for loop. Let me just move this a little further down. Just to... There, that should hopefully help a little bit with that. But yeah, notice how when I write my pseudocodes by braces, I use very similar kind of paradigm that you would use when you're writing some programming code. You want to make sure you line up your braces, that way it's easy for you to read them. Would it be possible to simply walk through steps of the insertion sort? Now, I'm working under the assumption that there is some basic understanding of insertion sort. Our purpose for this lecture, we will be talking about sorting algorithms later. So I will be reminding you of these sorting algorithms later on in the course. The point we're going to do is we're going to analyze this algorithm. So that's what we're going to be doing right now. We're going to talk about sorting actually probably in a couple weeks. So I'll be talking about this algorithm again. Just not in the same level of detail that you may have seen in 115, but I want to make sure you have the main understanding of the ideas when we get there, okay? Our purpose here is we're going to analyze this algorithm. Yeah, no worries, no worries. So the point here, like I said, it's not really about understanding insertion sort, it's about understanding the process. So if you were to analyze your algorithm, you understand the kind of the general steps. It's okay? Wonderful, wonderful. No worries, no, I appreciate the question. Okay, now this is a little bit more complicated than our previous example. It's actually a little bit more, at least. Okay, so we're going to pick up the same idea I did at the beginning of this lecture. So what I'm going to do is I'm going to try to group operations that all take a constant number of operations, which in total all take some constant number of operations overall. So notice that I have this for loop that seems to govern the outermost part of this, but notice that our worst case analysis, we're at the mercy of this while loop. This is going to play a very important role in our analysis. So you're going to notice that I'm going to give that a special name at some point. So the first thing I need to do is I'm going to try to formulate a basic complexity function, and then we're going to start trying to simplify and figure out what each part of this means. So first, you'll notice that everything outside of this while loop, but inside the for loop, all of this takes some constant number of operations, right? The assignment of x, the assignment of j, and the assignment of this array element, right? All of these take some constant number of operations. I'll call that C2. So there's some C2 number of operations that happen there. Notice that I have the same kind of idea here. Inside of my while loop, I have some C1 many operations that happen. So another constant number of operations. And I have a return statement at the end. Outside of the for loop, I'll see that that takes C3 many operations. There's some constant number of operations. So I've identified all the constant number of operations that are going to happen, at least for our purposes here. Now, I'm going to work my way inwards to outwards, but you'll notice that if you actually look at my analysis very carefully, you'll notice that the way I'm going to formulate it is I'll start at the outermost and work my way in. So you'll see what the way I count this, that, whoops, I lost my marker. Let me grab that. My apologies, everybody. The lid on this is a little loose. So if I were to count up all the operations associated with this while loop, this would be C1 times the number of iterations of the while loop. It's C1 times the number of iterations of the while loop. And if I wanted to take all of the operations that are inside the for loop, notice that if I were grouping all of these, if I take all of them, if I write that out over here, notice I have to take a whole bunch into account. To make this a little easier to see, I'm going to write it in black. So notice that I have some C1 operations times this amount of iterations for the while loop. I don't know how much that's going to be quite yet, right? Then I have some C2 number operations. And then notice that overall it performs it some number of times based on the for loop. The great thing about for loops is they're very easy to predict how long they're going to take because it tells you how many it's going to perform, how many iterations it's going to perform. But we'll get to there in a moment. So if I write this all out, I'll end up with C1 times the number of iterations of the while loop plus C2, right? That's all of these other ones here inside the for loop. So that's all of this. That's everything inside of my for loop. But it happens depending on the number of iterations of the for loop. So you'd multiply this all by the number of iterations of the for loop. So if I can break this down and figure out what those iterations are and then simplify, I'll have my complexity function. Are there any questions about how I did this? I must stress that if you find yourself a little bit like looking at this, like, okay, well, where did that come from? I do have a much more detailed explanation. In fact, when you're working on yours on the assignment, I encourage you to take a look at the way I drew it up in my notes. It makes things a little bit easier to see how you might formulate and write it and present it. But I just want to walk you through kind of the approach. So are there any questions about how I came up with this? Yes, thank you. We need C3 at the end. Thank you. So we need to add C3 somewhere. I'm just going to, but keep in mind, this is just the for loop. This is all the for loop. So if I want my complexity function, I take C3 plus this. Perfect, perfect. So it's just, so your complexity function will look like C3 plus all of this. And now the question is, how many iterations are happening with the while loop and how many iterations are happening with the for loop? If we could figure out those two pieces, then we have something we could simplify. Perfect, perfect. So now we got to figure out that part. That's the part where we have to use our noodle. We have to think about it. So it's okay if I proceed over to this board over here. Just want to make sure, because I have to kind of walk us through where some of these bits and pieces are going to come from. Okay, good. If not, like I say, you'll find that this is all fully worked out in the notes. So let's try to walk through the analysis of this. So I'm going to just proceed to where we have all of these bits and pieces. But we need to actually figure out the iterations of the loops, right? That's kind of an important part of this. So what are we going to do? Well, let's derive that. So, let's think about this. Observe that in the worst case, so this is because we're doing worst case analysis, observe that in the worst case, variable j begins at I minus 1 and goes down to 0. Now you might ask, why does it go down to 0? Because if you go back to the algorithm over there, remember what it does when it's in reverse sorted order. It will swap, it'll make way, so it'll be shuffling over all these elements all the way until it gets to the very, as far as left as possible. But what does that mean? It means it has to go all the way to the left. But the condition of the while loop gets falsified because of the condition that j has to be greater or equal to 0. So that will become false, and that's when this will stop. So if you actually were to play out with how many of these occur, doing this implies, or implying, the innermost loop iterates. So notice that I start off at I minus 1 and I go all the way down to 0. Yes, so that's what I was suggesting. Now, remember, we only really are going to count when the actual iteration occurs. So I'm just going to go and say, okay, so I'm going to pull out that tool I just gave you earlier. So notice that I start my upper limit. So what I start off at its highest value is I minus 1. And then I go down to 0. And then I'm going to add 1 because remember, like I said before, you want to make sure you keep the appropriate count of how many there are. Well, I minus 1 minus 0 plus 1. Well, I minus 1 plus 1 is just I, right? So the number of iterations is I times. So we've addressed the question of how many times that while loop is going to occur for each position I on the outermost loop. But now we'll look at it. It actually depends exactly on the outermost loop, on what I is. So that you're going to see how that some of those tools I showed you will pop up. So now that we have that, furthermore, the for loop starts at I is equal to 1 and goes up to n minus 1, right? Implying the worst case time complexity is, so now I'm going to write this out. Now to be very clear, remember I have all the bits and pieces over here. Now I'm just going to simplify it down. So I'm going to, everywhere where I had those things where I didn't know the answer, now I have the answers for both of the blanks I didn't know. I'm just going to insert them in, but I have to do it very carefully because remember now remember, the number of iterations for that while loop depends on I. And I is something that's controlled by the outermost loop, right? So you're going to see how this is going to get formulated as a summation. So just try to carefully follow what I'm up to. So remember, I have a C1 and I have a C2. But remember, the C1 is multiplied by the number of iterations of the while loop. So remember, the outermost loop starts at 1. So I'm going to have a sum starting at I is equal to 1, and it goes up to n minus 1. And then what's going to happen? It's going to take C1 times the number of iterations of the while loop, but that's I, right? So it's C1 times I plus C2. And then we have our C3 just kicking around outside of this whole thing. So this is actually the simplification of all that work I just did over there. So if you're wondering, okay, so you said you're going to multiply by the number of iterations of the loop. But notice all I'm doing is I'm adding over each case of the for loop on the outside. In fact, it's very natural if you think of it more like I'm carrying out the for loop. So what does the symbol represent? So remember, this is a summation here. This I here is the exact same I. So notice that I've used the same variable name as I did in the algorithm because it makes things a little easier for you to spot. So notice that my innermost loop actually iterates exactly I times. So all I've done is I've started I. Remember, I is actually the one that appears in the algorithm. So I starts at 1, and it goes up to and includes n minus 1. So each time this happens, I'm just going to consider each one of those as they occur. And for each one of them, it does a C1 many operations, like I had over there. But for each iteration of that while loop, it's going to perform it exactly I times. And then I'm going to have this extra C2 many operations that happen for that iteration of the for loop. So just to make sure we're all kind of walking on the same page here, let me walk back over here. Just to make sure everybody's sort of on the same footing here. Okay, so if you're looking at that summation over here, remember, this is just like I had earlier. So you start off as I is 1, and then you plug in what I is for what I appears here. So you'd have C1 times 1 plus C2. Then you would go to I is equal to 2, C1 times 2 plus C2. And so on and so on and so on, up until n minus 1. So just to reiterate, remember, the outermost loop goes from I is assigned to be 1 to n minus 1. Notice that that exactly appears over here with this summation over here. So notice that the number of iterations of the for loop dictates how many iterations happen with the while loop. Because remember, this while loop happens I times in the worst case. So I need some way of controlling that when I formulate the complexity function. So when you look at my sum over there, notice I have my C1 times the number of iterations of the while loop plus C2. That's exactly what I'm going to have over here. When I look at my complexity function, then I have my C3 sitting outside here. Correct. Yes. Yes, exactly. Exactly. So you'll notice the big observation we had here is that really when I go over the iterations of the for loop, they actually govern how many iterations happen with the while loop. So this sum here is really just telling me how many times I add this up, which is no different than me counting how many iterations happen. But now I need some way of saying, okay, when I is 1 in the algorithm over there, how many iterations happen in the while loop? I many. But there's C1 many of those operations times this. And that's our C2. That's the same one I had over there. And then the C3, that's from, remember, our return statement at the end. No, wonderful, wonderful. So now we have something we can play around with. This looks a little sophisticated at first, but watch this. Watch this. I'm going to show you a couple neat tricks with summations here. So first thing I can point out to you, and I do have a question. Yes, so keep in mind C2, it takes once per iteration. But remember, C2 happens in total, it's totally dependent by how many iterations there are of the for loop. So you're going to see that I'm going to split the sum over this addition over here to simplify it down, and then we're going to count up the parts separately. So I'm going to start up from I is equal to 1 to n minus 1. I'm going to have C1 times I. This is going to be one sum. Then I'm going to sum up. So keep in mind, so one property of summations is that you could distribute them over addition like this. So I'm going to sum from I is equal to 1 to n minus 1 of C2. So these I have two sums. I split that apart, and then I have C3 just sitting on its own. So now what I'm going to do is I'm going to simplify each of those summations. Now the great part is that every single time this occurs, notice it's C1 times I. I would like to make it look like what I had on the board earlier in the lecture. But notice every single time I have C1 times I, but that happens every single time, right? So I may as well factor it out of the summation. Just like what I did when I was showing you how I justified the second closed form for you. My apologies there. I sort of slipped. So I got C1 times the sum from I is equal to 1 to n minus 1 of I. So all I'm doing is I'm factoring out the C1 because it's not dependent on I at all. But every time I multiply I by C1, it's no different than when I gave you that rationale earlier about, okay, so if I'm going to multiply everything by 4, it doesn't make any difference. I just need to know how many times I need to multiply by 4. So I can do the exact same thing for the second sum, the one I have right here. So notice I have C2, where I start this at I is equal to 1 to n minus 1 of 1. And then I have my C3 just sitting out over here. Now, here's the neat part. Once you're at this stage, you can see right away that we have our tools that we were looking at before, our closed forms. Does everybody see them? There's one right here, and there's one right there. There's the first one and the second one, respectively. So all I do is I apply those. So here we go. So I'm going to have C1 times, now remember, the way that I gave it to you was, it was the upper limit times the upper limit of the summation plus 1 divided by 2, right? But notice that the upper limit here is n minus 1. So it's going to be n minus 1 times n minus 1 plus 1, which is just n. Then you divide that by 2. So I have n minus 1 times n divided by 2 plus C2. Then now I have this closed form. I know how to do this one. I take n minus 1, I subtract 1. N minus 1, subtract 1, and then I plus 1. And then I have C3 still kicking around. So now I'm just going to simplify a little further down. Now, is it okay if I move over to this board, everybody? Just because I want to make sure we have a little bit more space. Okay, good. Excellent. I do have a question while the board is, well, this lovely camera friend is kind of moving around here. Would anybody want to, so the last step, let me just head back over there. So let me just note it here. I do have a question while we're getting over here. So just to reiterate what I have down here, it's C1 times n minus 1 times n over 2. This n minus 1 times n over 2 came out of the simplification of this summation. That was where we used the first closed form I had before. Then I have C2 times n minus 1 minus 1 plus 1. This is the application of the closed form I gave you, the second one, right here. And then I have C3, it's just sitting there. So I do have a quick question. For anybody that's never seen these summations before, would like me to put like a little optional reading with some little exercises so you can see how you can manipulate summations like this? I'm happy to make one and prepare it for you. Yep, I can happily have that ready for you after class, okay? Now, wonderful. Yeah, so I will also include some tips in there so it makes it a little easier to play around with some of these. So I'll include some little tips and tricks and a list of these closed forms for you. So somebody was asking, wasn't the formula n times n plus 1 over 2? That was when n was the upper limit of the sum. Now the upper limit of the sum is n minus 1. So wherever you see n, you put n minus 1. And you'll notice that you get n minus 1 times n minus 1 plus 1 divided by 2, which that simplifies to n minus 1 times n divided by 2. Wonderful, wonderful. I just want to make sure we're walking through this carefully. Okay, so now let's simplify this down. We're just about to the end. So we're just being very careful. So let me write this out a little bit easier for us. Okay. So once you do that, you're going to end up with C1 divided by 2 times n squared plus n plus C2 times n minus 1 plus C3. Now I have a question for you. For those that are familiar with big O notation, what would you tell me this is big O of? It's quadratic. Because notice that the most dominant term I have here is this n squared here. So you would say, which is big O of n squared. But we haven't really talked about big O quite yet. But yes, so this is one way you can derive the analysis for insertion sort and why it takes quadratic time. So we would say that this takes quadratic time. Wonderful, wonderful. I'm going to include in the notes another method of approaching this, where what you do is identify the operation that happens the most frequently, you count that one, and you can simplify the analysis a little further, but I will warn you, if you take this approach, it often is very specialized. You have to be very careful what you count. So I'll include it in the notes if you want to take a look at it. It's another way you can analyze an algorithm. But the big question, somebody's asking, shouldn't it be n squared minus n? N squared minus n. I think, let's see, we got C1 times, so we got n, we got n squared. Yeah, I think you're right. Thank you. Yeah, because we had n times n minus 1. So that would be n squared minus n. Thank you. Wonderful. Okay, so I have a question for you. When you think about the input size, when we had all these values of n, notice I have all these constants here. If I give you some problem and I want to compare two different algorithms, I'd like some way of telling me for sufficiently large, that means a big enough n, so that I could tell you this algorithm is more efficient than another algorithm. So you can always walk through a little exercise. I'm going to include a picture in the notes of a table that does this. But if I give you two complexity functions, as the input size grows, there's going to be some of these terms that become irrelevant. Because the most dominant terms, like this n squared here, become what we would say it dominates the running time. So that's why, for example, when I write out something like big O of n squared, if I compare it against something that says big O of n, like a linear function, you'll see for a large enough n, that the n squared functions that I give you, for some point I'm going to call n0, there's going to be some point where one is going to beat out the other. So there's two kind of bits and pieces here. I would like to have some way of talking about all possible implementations of my algorithms. Well, remember, these constant number of operations, they may actually represent CPU cycles of the computer. But I don't know what my computer specifications are. I'm taking a machine-independent approach. I don't know how many operations those are. I just know there's some constant number of operations. But they may vary from computer to computer. I would like some way, using the dreaded M word, the mayonnaise, I would like some very natural way to capture all of the possible ways these constants could take a value, plus this phenomenon that I just drew upon, is that very often when you have one algorithm versus another, for very small inputs, some algorithms perform much better than other algorithms. However, they do not necessarily tell you the overall behavior over all the problem instances. So for example, if I give you an algorithm like bubble sort, oftentimes somebody tells you, bubble sort, yeah, that's a really fun algorithm. But for very small inputs, bubble sort is actually rather effective. But there's going to be some point where an algorithm comes along with a better big O, which I'll talk more about. If it has a better big O, for a sufficiently large n, that algorithm is no longer going to be as effective as the one with the better big O result. I would like some way of talking about that. So that brings me to talking about growth rates of functions. Which I'll also call asymptotics. So this is another subject we're going to be playing around with. So when I play around with this, we're going to be using what is called big O notation. Now you may have seen this before. We're going to define big O notation for us formally. So we're going to actually write out what the proper definition of big O is, and we're going to play around with it probably next class. So I'm going to write out the definition, but for historical purposes, I feel like I need to point out that big O notation wasn't just a construction for algorithm analysis. It's been used for quite a number of years for analysis generally. It was introduced, say, in the early 20th century, I think like around the early 1900s, by Landau. And it's often used for studying, for example, the tendencies when you have an input of a function that gets really, really big, the patterns that arise when you count up or try to count some elementary object. So for example, tendencies of prime numbers, or sometimes you have this extra term that's kicking around in your analysis that you really just want to keep a track of, but it's not very important. This is how sometimes it pops up. In our case, we're going to use big O notation in a very natural way to help us classify and determine which algorithms are more efficient than other algorithms for all our problem inputs. Okay? So let's define big O. So here's the definition of big O. So remember I talked about complexity functions earlier. So I'm going to say let f and g be complexity functions. So I'm going to have two complexity functions. I'm going to call f and g. I'm going to say that f, where its input is n, is big O of g. So often when I see this, I'll say is or is in. Is big O of g if and only if, that means whatever, if and only if and only if, so if I tell you that f is big O of g, whatever follows from after this line has to also be true. If anything over here is false, then f is not big O of g. So, if and only if there exists Now, sometimes people like to abbreviate there exists with a backwards capital E. So if you ever see a backwards capital E, that's an abbreviation from logic that says there exists. There exists some positive real constant C. So it's going to be two constants. There's one called C and a positive integer constant n0. So it means it's going to take on a value 1 or more. So 1, 2, 3, some value like that, n0, such that for all n greater or equal to n0. So after this point, now some people, when they say for all, they often will write a upside down capital A as an abbreviation for this. Another symbol from logic. For all n greater or equal to n0, we'll say that f of n is less than or equal to c times g of n. So you might look at this definition and say, Dan, what is this? What is this? Okay, there's two things I want to point out for you. The first one is that there are two constants, this c and this n0. And then what happens is there's going to exist these two constants. So very often when we use this definition, when we try to prove things about big O, we'll try to find these two constants so that this inequality holds. The f of n is less or equal to c times g of n, but this inequality has to hold for all n greater or equal to n0. You might ask, Dan, why is this definition relevant for us? Well, it's two things. Now remember the two phenomena I pointed out to you just a moment ago, that very often for our computers, we would have it where we have those constant number of operations, right? When we count the operations, they take some constant number of operations. So notice that the C here is quite similar to that. You can think of it almost like the speed of the operations. But also, there's going to be some point where there may be a potential trade-off because of overhead of one algorithm versus another algorithm. So notice that this is the point of n0. So very often you'll find that one algorithm might perform better for smaller inputs than another algorithm, but after that point, it's just unanimous which one is the better algorithm. So both of these are captured in this definition. So I'm hoping I motivated why this might be a little bit, even though it looks a little abstract, for those that may recall back to their calculus and see maybe a formal definition of a limit, this definition looks kind of like that one. It's not exactly the same, but it's quite similar. So that being said, I have to stop for today. When we come back, we'll talk about big O. We'll prove some examples with big O. We'll try to show some functions are big O of another and see some examples where f is not big O of another, and we'll see some properties that big O has. If not, I would have happily talked more about it, but we're out of time here for today. So I will include in the notes what I'll be talking about next time if you want to get a little ahead of the game and start working on problem number 2. If not, we'll talk more about it on Thursday, okay, everybody? So I'll say thank you very much and have yourself a beautiful day. I'll see you later.